Hello and welcome back. Logic Theory Part 2, Logical Equivalences. Logical equivalences, we have two compound propositions, P and Q, and we say that P and Q are equivalent if P and Q have the same truth values. Very simple. So here's an example. P implies Q is equivalent to not P or Q. So the way to see this is to use the truth table. P and Q, P, true, true, false, false, true, false, true, false. So these are the four possible combinations of the values of P and Q. So there's not P here, just negation of P. True, false, true, false, false, true, false, true. P implies Q. Again, let's remind you, we do not allow truth to imply false. Truth imply false? No, false. Everything else is true. It's fine. True implies true is true. False implies true is true. False implies false is true. Now, you have not P or Q, not P or Q. When one of them is true, you get a true. This is true. False. True. True. And you see that these two are the same. So P implies Q is equivalent to not P or Q. And this is very important because when you are kind of dealing with complicated expressions, if you have something like that in the expression, you can replace it with this, which is easier to work with than the implication itself. We have two famous laws called DeMorgans laws. The negation of not P or Q is not P and not Q. Not P and Q is not P or not Q. So you see, you negate each term, and the or becomes and the and becomes or. So if you look at this table, I'm going to prove both of them actually are proven here. So again, here's your P, here's your Q. You get not P, not Q, because we have in this here we have P, we have Q, we have not P, not Q, we have P or Q, we have P and Q, and we have this. So we create a table to do these two equivalences at the same time. And very simple, just apply that definition. P and Q is true when both are true, see? True, 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 and then everything else is false. P or Q is true if one of them is true. True, true, true. Now, the negation of P and Q, here's P and Q, you want to make the negation of P and Q, true becomes false, false becomes true, false becomes true, false becomes true. And if you get not P or not Q, not P or not Q is true when both are true, this is false. When at least one of them is true. This here is true, this is true, this here is true. And the same thing you find the other DeMorgans laws. Distributive laws. This is, to remember that what we're doing is like in arithmetic, you can have, you can have 3 times 4 plus 5 is equal to, you multiply 3 by 4 and 3 by 5, and you put plus in the middle. So 3 times 4 plus 3 times 5. And that's called distributive law. It applies to both the or and the and. So how do you prove any one of these laws? Well, just create this, this table. Now you have 3 variables, P, Q, and R, so you will have 8 different combinations of the values of these 3 variables that they can take. So you create 4 T's followed by 4 F's, 2 T's, 2 F's, 2 T's, 2 F's, TF, TF. Once you have this, the rest of it is really applying the definition. Q or R is true when one of them is, at least one of them is true. So look at Q and R here. True, 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 false. True, 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 Q or R, true, false. Now you want to have Q or R here, P here, P and. So now we are doing P and Q or R. So we're doing this with an and. So true and true is true, true and true is true, true and true is true, true and false is false, false and true is false, false and true is false. So you get this here. You find P and Q, you find P and R, and then you take all of these two columns, and you get exactly the same answer as here. These are the same. So we proved this equivalence right there. Now let's prove that implication is not associative, meaning the order is important. You can't take, I will take the parentheses out. So P implies Q implies R is not equivalent to P implies Q implies R. How do we do that? Let's use the table again. I have 3 variables, so I need 8 rows. So you get 4 T's, 4 F's, 2 T's, 2 F's, TF, etc. Now first P implies Q. Again, the rule is we do not allow truth to imply false. So there's 3 columns here, these 2 columns. True implies true, yes. True implies true, yes. True implies false, no. True implies false, no. False implies true, yes. False implies true, yes. False implies false, yes. False implies false, yes. So that's P implies Q. Now we need to do P implies Q implies R. So we are going now this way. P implies Q implies R. So true implies true, yes. True implies false, no. False implies true, yes. False implies false, yes. True implies true, yes. True implies false, no. True implies true, yes. True implies false, no. Then you do Q implies R. Again, true implies true, yes. True implies false, no. False implies true, yes. False implies false, yes. True implies true, yes. True implies false, no. False implies true, yes. False implies false, yes. And then you take now P implies R. You need P implies this. So you need to go now from here, here to here, like that. Is true implies true? Yes. Is true implies false? No. Is true implies true? Yes. Is true implies true? Yes. False implies true? Yes. False implies false? Yes. False implies true? False? Yes. And false implies true is true. So when you notice these 2 columns, these values are not the same. So these 2 columns are not the same. So these are not equivalent. These are not equivalent. So again, implication is not associative. Here are important logical equivalences. They have some names. You really need to understand what they're doing. They're really simple. Double negation, not P is P. Identity P and true is the same as P. P will determine, because if P is true, true and true, you get true, which is P. If P is false, false and true, you get false, which is the same as P. Domination, P or true is true, because when the or is true is at least one of them is true. P and F is false, no matter what is the value of F. And you keep going. Associative, commutative, we know what that means. Distributive, we know what that means. We just did one of them earlier. DeMorgan, Those are the DeMorgans laws. And this is the negation laws. P or not P is always true. And P and not P is always false. And this one, we are calling it convergent. And we proved it a little bit earlier. Very important one to use in complicated expressions. Proof without the use of truth tables. If you feel comfortable, you can sometimes prove equivalences without the use of truth tables. So let's prove here that these two are equivalent. So normally you take the side that is more complicated, try to play with it to see if you can get it to be equal to the other side. Here I'm going to start with the left-hand side. Left-hand side, we're going to apply the DeMorgans laws first. So actually we need to apply the DeMorgans laws first. See, we have P or not P and P or Q. So we apply the DeMorgans law first. Now we reach to this point. Now P or not P is true. That is P or not P is true. That's a negation, see? So negation, we apply the negation on this here and we get true. Now true and something is something. Is that something? True and P is P. That's called identity. So true and all of this is all of this. Now we're going to apply the DeMorgans law a second time, not P and not Q, which is the right-hand side. This is a little bit, might be a little bit difficult to understand, but I think we can make it easy as possible. We're going to be using P and not P as being the logical atomic variables. And we are going to use something called disjunctive normal form. Disjunctive normal form, DNF. It's, to remember it, is sum of products. Sum of products. So this one is a compound proposition written as sum. Sum is or, okay? Of products. Products are ands. Of one or more literals. Here are examples. See how this expression is written? Or, and then in every parenthesis here you have ands. Those are the ands. The ands or the variable by itself is fine. This one is okay. You have an expression here. One expression is fine. That's DNF. Here is an example how to do that. You really need to pay attention because it's not that complicated once you understand it. Write P implies Q in DNF. Okay. What you do is create first the truth table of P implies Q. That's where the truth table, right there. And look at where this expression is true. This, and this. This, and this. When I look at this, T, I'll put P and Q. When I look at this, FT, I'll put not P and Q. When I get this T, I get not P and not Q. Technically, what I'm saying is, when is this true is when both Q is false and P is false. That gives you not Q is true and not P is true. Then it becomes true. That's what we're doing here. Here, when is this expression true is when P is false. Because not P is true and Q is true, you get true. So once you have that, then you put or between these three expressions here, three propositions. So the answer will be P implies Q is equivalent to P and Q, or not P and Q, or not P and not Q. So we wrote it as sum of products, product. But you know also, you noticed earlier we proved that P implies Q is not P or Q. So that's another way of writing the same expression as in DNF. Now the other form is called conjunctive normal form. Conjunctive normal form, CNF, is a product of sums. The same situation here. It's a compound proposition written as product and of sums, ors, of one or more difference. Here's an example in CNF. P or Q or not or and, P or Q and, see, and every term here has only or inside it, or the variable itself. This one is fine, only one of them, that's also fine, is written in CNF. Now, I want you to think of the following. Think at and as a multiplication, and or as an addition. Excuse me. And T as 1 and F as 0, not 1, the negation of 1 is 0, the negation of 0 is 1. Okay, look at this expression here. This expression here is false if each one of this must be false. This must be false, this must be false, this must be false to get a false answer. Because if one of them is true, you get a true. Okay, so this one is false if and only if P is false, Q is false, and R is false. Now look at this here. It's false if P is false, Q is false, and R is true. Because you want not R to be false. This one, it's false if and only if P is true, Q is false, and R is true. Look at this now. When is this going to be true? If P is true, Q is true, and R is true. Then you get true. You have to have 1 times 1 times 1 to get 1. If one of them is 0, you get 0. So this is true if P is true, Q is true, and R is true. Look at this here. When is it true? When P is true, Q is true, not R is true, meaning R is false. Meaning R is false. Look at this one here. Not P and Q and not R. This is true when this one is true, which means P is false. This one is true. This one is true, meaning R is false. So look what happened now. We are going to write P by conditional Q in CNF. Okay? So first method is put P by conditional Q, and take the negation of this, not P by conditional Q. So you have true, 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 false. Okay, we have that, we know. Now you are negating this, you get this here. Now you look again at the true, and we did exactly as we did before. It's the sum of product now. We're making it as sum of product first. Making what? This here, the negation of the proposition that we are interested into. So you get P and not Q, not P and Q. So you put or between them. So now, not P by conditional Q is this or this. Now you take another negation. You negate this again. So you negate this again, you get P or P by conditional Q. When you negate this, so you are negating all of this. You are negating all of this. So we're going to use DeMorgans Law. So you use DeMorgans Law now. You say not this and not this. So we're going to be doing it down here. So not P and not Q, or that's what I'm negating. This is this one here. Now look at here. We are going to put not this and not this. When you put not this, you apply DeMorgans Law a second time. So that's not P or not Q is Q. This becomes and not P is P or not Q. So now I wrote this expression as product of sums. Product of sums. That's first method. Second method is do not use do not take the negation of P by conditional Q, just leave it alone. And now instead of looking at the T, look at the F's. Instead of looking at the T, look at the F's. This F and this F. Now remember, we are going to do this as product of sums. So now this F coming from this and this, that would be not P or Q. This here will be false if both of them, if Q is false and not P is false, which means P is true. Same thing here. F is coming from these two here, so you put P or not Q, and then you put the and between these two, and you find the same answer. This is a little bit easier than the one that we did earlier. And that is the end of logic theory part